Hello everyone, thanks for attending this session. This will be on Optimizer. I'm Boris, I'm a principal engineer at Anaplan. I work on Anaplan's core calculation engine. I've been here for about 3 years. And we'll be looking at the internals of Optimizer. So something about how it works under the hood, how linear programming relates to what you see in the Anaplan UI, hopefully to give you a better understanding of how to build optimization models in Anaplan. We'll be covering a few topics, for example, starting with what a linear program is in a mathematical sense, going into how that works in Anaplan and how it gets transformed into an Anaplan model. We'll be looking a bit at how to measure the size of a problem. So I know that's an issue that people have. They don't quite understand how big a problem is when it becomes an optimizer problem. And then we'll be looking a bit about how to structure certain constructs within Anaplan. And then a few links to further reading. So a linear program is literally just this. That's all it is, very simple. 3 things, 6 terms, and it looks perhaps much simpler than it is. Maybe it's a bit deceiving. So let's try and pick it apart term by term to work out exactly what we're getting at here. The most important thing here is x. Find x, it's always x. So we have 3 x's here, one on each equation. And that makes sense because x is the sort of the variable we're trying to discover. But because this is not a scalar problem, x is actually a vector. So when you see x in these slides, imagine not an x, but actually more like a line item. So x is a number of unknowns of a certain size. And we represent that with these curly brackets and these commas. The next piece of the puzzle is the objective. So in the canonical form, we are always maximizing. This is simply because you can make any minimization and maximization by flipping the sign and timesing everything by -1. And we're maximizing this very strange looking thing, CTX. So that doesn't look like an equation at all, really. And that's because C, again, is a vector. So we have 2 vectors. That doesn't really tell the whole story. So how do we take these 2 vectors and turn them into something resembling an equation? Let's imagine for a second that we have these 2 vectors, and one of them, C, is 4, -2, and 7. So imagine it's a line item. It's dimensional on a list with 3 items in it. And X is similarly a vector, but it's of unknowns. So we can call them x0, x1, and x2. And we want to maximize this objective. So what we actually do is we multiply these 2 vectors together into what is essentially a dot product. So we take 4x0, the -2 becomes -2x1, and the 7 becomes 7x2. So actually we're maximizing this equation, and that makes a lot more sense. In terms of what a linear program is. So this is our function that we're seeking to maximize. This is our goal. This is our profit or our minimizing cost or something like that. The next important piece in linear programming is the constraint. Now, again, in our simple canonical formulation, the constraint is a single equation, ax less than or equal to b. Again, the sense or the sign of the inequality doesn't really matter because you can flip that with a multiplication by -1. But the interesting part is this ax, because it's a capital A, and that means it's a matrix. So you may have learnt about matrices at school, and you may have learnt them in Anaplan. And in fact, Anaplan is, in many ways, all matrix-based. We have Hyperblock, which is essentially an n-dimensional matrix engine. And your matrix A is the matrix of coefficients for the equation. So A represents all of the different pieces of your constraints. And its dimensionality is a row for every constraint, and it's a column for every variable. So this, as we'll see later, does drive the size of your problem. And we can index the bits of A by using this sort of two numbers and a comma syntax. So the top leftmost A is A00, and the bottom rightmost A is ACN. So C is the number of constraints, and N is the number of variables. We also had a B in there, and B is another vector. We're getting pretty good at vectors these days. So when you take that and you blow it out to constraints, what you're actually doing is, again, a multiplication. But this time it's a matrix multiplication. So it's a bit trickier. But you can see the same logic happening. You essentially take your X and you apply it to every row in A. And you take your B, and that becomes the other side of the inequality. And now we can see a more familiar formulation of constraints. So we can see that for the first row of A, 1, 4, minus 5, we multiply that with our x's to get 1x0, 4x1, and minus 5x2. And then we take the first item in the B vector and make that the other side of the inequality. So we end up with x0 plus 4x1 minus 5x2 is less than or equal to 1. And we do the same for the other two rows. Now the last row has a little gotcha in there because there's a 0 in our A. So what that does is essentially it times that particular variable by 0, which drops it out of the constraint entirely. So in linear programming terms, you never have constraints that don't apply to all the variables. Just sometimes they apply to 0 times the variable. And that, again, will drive the size calculation we'll see a bit later. So the last term in our linear program, you'll be thankful to know, is a little bit simpler. All this says is that all x's are greater than 0. This isn't necessarily that relevant in the Anaplan linear programming sense because we give you the ability to set your bounds for your x's or variables. And by default, if they're unset, we'll actually drop that to negative infinity for you. But in the canonical formulation, if you've not set any bounds for your variable, it's bounded from below by 0 and from above by positive infinity. And that mainly is convention. So moving on to Anaplan, a territory where I guess we should all be more familiar. Let's start by building a small model. Let's build a list A, list B, and a list C. And let's have those lists be 3 items each, mainly because if I had any more items, the formulas wouldn't fit on these slides, and that would look very silly. So list A has 3 terms, A0, A1, A2. List B and list C, very similar in that regard. And when we declare a line item, in these slides, I'm going to use the notation in square brackets of the lists that line item is dimensioned by. So in this example, we have a line item price, which is dimensioned by list A and list B. So there are 9 terms in price, and those will be 1 for each A-B combination. So how do we map this to what we saw earlier? So our variable in Optimizer is actually a line item, and it's a single line item. And we'll be looking at what happens when you have a single variable, again because any more variables wouldn't fit very well on the slides, but also because it's just a question of extending this logic to multiple terms. It's not a particularly massive leap to get to multiple variables. So we'll start with our variable, we'll call it capital X, and we'll dimension it by list A and list B. So again, this means we have a line item X, dimensioned by list A and list B. List A and list B each have 3 terms. And so the objective is the goal of the optimization. So the objective doesn't have a right-hand side, it only has a left-hand side. And in Anaplan, this is represented as a numeric line item that has a formula that is of the form coefficient times variable, potentially multiple times, multiple coefficients and multiple variables. And you select minimization or maximization. And it must have a top-level summary method of sum, because it will add up all of the values to give you a single number that will be the value of the optimization. So this will be what we're maximizing or minimizing, this single number. And what's interesting is then, how does Anaplan get to that single number? And Optimizer will use the same logic that Anaplan does to do that top-level aggregation. So in this situation, if we have an objective dimension by list B, and we have X on list A and list B, and we have C on list B and list C, so we have a single common dimension between X and C, and we have two different dimensions, but the dimensionality of our constraint is that same common dimension. What Anaplan will do is roughly this equation here. And the notation that I've used is a line item with square brackets, and terms is that cell in a line item. So C, B0, C0 is the line item C and the term at B0, C0. And what you can see here is that we will, for each of items in list B, work out the aggregation of X on list A and C on list C, and then we'll sum those for each term in list B. So we end up with 3 fairly long terms, and each of those are a C times an X, but that C times an X is all of the C's in a particular row or column of your line item. And this is quite important to bear in mind when you declare an objective, because this aggregation is what drives Optimizer. So what you can see here is actually you're aggregating your C's and aggregating your X's separately across the external dimensions. And that's not necessarily what you want. You might want to multiply each X separately, for example. So you have to bear in mind the dimensionality of your objective and the dimensionality of the variables you're using in that objective when you build your problem. This becomes much more evident when we get to the constraints. So the constraints, again, Anaplan supports multiple of them. We'll look at a single constraint. And again, a constraint in Optimizer is just an Anaplan line item. So all you have to do is declare a line item and set it as a constraint in the Optimizer dialog. And that constraint must have a number of properties. That constraint must be a Boolean valued line item. And it again must have a top-level summary of all or any. And again, the formulation must be constant times variable. So in this situation, we've used A as our constant and X as our variable. And a constraint, because it's a Boolean valued line item, has to have a formula that results in a Boolean. And to achieve that, you would put a greater than or equals to and some other line item, or a constant. In this case, you've used a line item B. Optimizer will only support greater than or equal to, or less than or equal to, or equal to. It won't support strictly greater than or strictly less than. That's for fundamental constraints in the optimization algorithms we use. But what the result of this constraint, again, needs to be unrolled to turn it into that form we saw earlier. So when you take your constraint and you dimension it by a list C in this case, what that tells Optimizer is to create a separate constraint for each item in list C. So this constraint will actually be 3 constraints, one for C0, one for C1, and one for C2. Now for each of those, we then evaluate at that list C term the rest of the formula. So in this case, we can see B is dimensioned on list C, but the other 2 terms are independent. So actually what we'll end up with is 3 constraints that have the entirety of the left-hand side the same and a different value on the right-hand side. And you can see the unrolling happening here again, because A is dimensioned on B0 and X on list A and list B. When you unroll those, you end up summing X over list A and then multiplying that with the appropriate term in list B for A, and doing that for each of the 3 terms. And what you can also see is this constraint isn't particularly helpful, because what you've ended up with is the variable part of your constraint being identical and the constant part changing. So again, this is another very important thing to bear in mind, that when you unroll your constraints, when you dimension your constraints by any line item, any list, sorry, that isn't a unit list, you need to make sure that that's what your intent was, that you want a constraint for every item in that list. And that comes to how big is a problem. So back to our original formulation, we can see that the objective is always just the size of the number of variables. And we can see that the last term doesn't really bear an impact on the Anaplan formulation. So it's the middle term, the constraint term, that is the main driver of size. And it's that capital A that is actually the big determinant. Now, A must be a full matrix in the optimizer underlying implementation. And that full matrix must have a row for each constraint and a column for each variable. So the size of your problem is the size of that matrix. Now, when you have one variable, that's fairly simple. But when you have multiple variables, and if those variables are dimensioned by different lists, you're going to have to multiply together the number of cells in each variable you've used, and that will be the number of columns you have. So you can see that if you declare multiple variables, you're very quickly going to blow your problem out to be very large. So again, you need to consider carefully whether you actually need those variables or whether you can somehow express the intent of the problem without declaring them. And similarly, you need a row for every constraint. So the previous slide with the slightly silly constraints, you would still have to have 3 rows, and those rows would only be removed later in the pruning stage. But the size of the problem would still have those in there. So it would still drive the amount of data that needs to be shipped and the amount of computation that needs to be done. So this is how you determine the size of a problem. So what we're going to look at next is logical operators. So we talked a lot about numbers, and we talked about summing and multiplying, we talked about greater than or equal to and less than or equal to, but we didn't talk about and or. And a question I get quite a lot is, how do I do and or in Optimizer? I can't type it in the formula, Optimizer errors out. I can't use and or in my equations, and therefore I can't express my intent to optimize. I can't optimize only using this factory or that factory. And this is, I guess, because optimization is somewhat of a mismatch to how Anaplan represents data. Optimization is completely numeric, and Anaplan treats data, Boolean data specifically, specially. So to do optimizations, we convert Booleans into numbers, and then all your logical operators are simply mathematics. So I guess the question is, what does that mean? So when we look at and we have a representation of 0, 1 for our Booleans, then what and means is that all of those Booleans equal 1. So that means that the sum of those values is equal to the number of values there are. Or is that it's greater than or equal to 1, so you have at least one of them being true. And XOR, which is an exclusive OR, so that's at most 1 factory, for example, is actually just they equal 1 exactly. And the other thing to bear in mind here is that when we looked at constraints in Anaplan, we looked at how Anaplan adds up those numbers. So you can use Anaplan aggregation to drive these values out of your problem without you having to dimension by constraints explicitly. You can do get Anaplan to do a lot of the work for you. So let's look at an example. So this is a constraint mentioned on list B. We have x on list A and list B, and we set it equal to 1. So we're saying x, list A, list B, equals 1. So as we said, we would unroll that for each item in list B, and we have 3 constraints for B0, B1, and B2. And what we actually then do, as we've seen, is that we unroll for each term across the A dimension. So we would see that for the first constraint, xa0, xa1, and xa2, all in the B0 row, are equal to 1. So what we've written with this simple constraint is that for every x in the A column, for example, one of them must be set, and we do that across all of the rows. And this constraint could be used to model something like production. Say that we can only produce a good in a single factory. Or we could model something like demand, that we can't produce a good more than once, for example. And if we were to make a very minor change to that constraint, we were to say equals 2, we actually end up with exactly the same formulations on the previous slide, with a 2 on the other side. Now, in Boolean logic, what that actually means is that any 2 terms of those 3 can be true. And so actually you've expressed a fairly complicated Boolean formula just with a very simple Anaplan formula. So again, it helps to bear in mind what Anaplan's formulation is when you write your constraints. So the final topic we're going to look at is one that's possibly a bit more complicated. So we're going to take a bit of time to pick this apart. But this is what I've called fancy constraints, but actually what they're called are conditional constraints. So they are fancy because they allow you to use conditions, your favorite or from Anaplan formulae, in constraints, but only under very specific circumstances. And these allow you to drastically cut down the size of your problem. So imagine you have a constraint, but you only need to apply it sometimes. An example I worked on very recently was that you could only assign a sales lead to a sales rep if they were in the same area. So you couldn't assign a sales lead to a EMEA sales rep if the sales lead was in APAC, because that just wouldn't work. Now what you notice about this formulation is that the condition is static. The lead and the rep and their location is not determined by the model, the assignment is. So this means that if we have the criteria by which we want to exclude the constraint from the problem outside of the determination of the problem, we can actually model that in Anaplan and we can get optimized to drop those constraints out of the problem. So this is what that formulation would look like. We have what we call the condition and we have the constraint. So on the left-hand side of the OR, we have the condition, and on the right-hand side, we have the constraint. So the condition is lead location equals rep location. So I'm assuming here that these are list formatted line items and they're dimensioned on leads and reps. List A and list B would be leads and reps in this example. And we can test them for equality. And this condition is not dependent on X. So there's no X term featured in here, and there can't be an X term featured anywhere up the formula hierarchy of those line items. So this condition is static. It's fully determinable when you run the problem and not needing to be determined during the problem execution. On the other side, we have our constraint, which we saw before, X equals 1. So this is our constraint because our constraint is on list B, that we can only have a lead assigned to one rep, which makes sense as a constraint, I suppose. So what does this actually mean? Well, if we break apart the Boolean logic, what we're saying is that when lead location equals rep location, then the whole conditional constraint formula must be true. So we don't need to check the other side. So because we can statically determine whether this is true or not, we can skip the constraint on the other side because it doesn't matter what we set X to, it will always be false or always be true. And it is always true because of OR. So true or true is true, and true or false is also true because we only require one true. So we can actually skip the evaluation of this whole constraint just by using this condition. And when it's not true, then we know we need to look at the other side. We need to look at the constraint, and then we need to evaluate it in Optimizer. So this formulation of constraints allows you to make your problem much smaller if you have constraints that need to be driven by model logic. So that's all I wanted to cover today, and I have a few requests for you, which is that you watch the video from Singapore on Optimizer, because that has some more background in what Optimizer solves problem-wise, rather than this mathematical side of things. There are some exercises on Anapedia that you can try out, and there's some best practices as well. The exercises will allow you to try out simple problems and see if you can get them to work, and maybe you can apply some of these ideas to improve those simple problems, to make them more efficient. That's an exercise left to the reader or the watcher.